we're going to talk a little bit about motion of a particle in a fluid. Okay. So when we look at this title, right, motion of a particle in a fluid, do you come across cases where you see motion of particles in a fluid? I mean, I'm talking a particle, but in a general sense, okay, it could be a object, right? It could be any object. Okay, it could be any object. Can you think of examples where you come across motion of objects in a fluid? Yes, right? Some examples? I'm sure all of you know, right? Some examples of let's say submarine, right? So if you have a submarine in a in like say sea, for example, right, it's moving underwater, right? Right? A lot of aquatic life. Okay, it could be whale, right? It could be fish, right? Or it could be any other thing. Okay. You also come across motion of bacteria in a fluid, right? Plus, if somebody is interested in swimming, right, you can think about swimming of people in a fluid, right? So there are a lot of instances where motion of an object or a particle comes into picture. Okay. I'm going to ask you to do a simple calculation. Okay. Let's think about I'm going to have a table. Okay. I'm going to say this is going to be your object. Okay. Let's take 3 cases, maybe 4 cases. A whale. Okay. And let's think about a human or a man. Okay. And let's take a bacteria. Okay. They're all swimming in water. Okay. And the properties of water, like say it's ambient temperature. So your rho is going to be 1000 kg per meter cube is the density of water, and your viscosity. What's the value of viscosity of water 25 degrees centigrade? It is 1 into 10 power minus 3 Pascal second, right? That's your viscosity. Okay, so okay, now let's think about the characteristic features of these objects. Okay, let's say that, what do you think is the dimension of whale? Characteristic dimension. What do you think is the dimension of whale? Typical dimensions? 20 meters, right? It's tens of meters. Let's say we can approximate it to be something like say 10 meters. Okay, if the order of meters. Okay, so let's say it's 10 meters. What about humans? Was that roughly again, let's say of the order of meter, right? 1 meter, right? It's of the order of meter. What about bacteria? What is that? What do you think would be the size of the bacteria? What is that? Micron, right? Typical length scale could be of the order of say 1 micrometer. Okay, there are a lot of bacteria, there are a lot of viruses. Okay, and typical dimensions of these things are of the order of a micrometer. That's your characteristic dimension. What do you think about the characteristic velocity with which these things move? What do you think would be the speed of, let's say bacteria? What do you think would be the speed? Okay, so they typically swim with a velocity which is of the order of say 10 micrometer per second. Okay, that's the speed with which they move in a fluid. Okay, what about humans? What is that? 3-4 meter per. It depends on from person to person. So if somebody is a great swimmer, they will do little faster, right? So typically again it's going to be something like 1 meter per second. that's the velocity. Okay, you can kind of swim the length of your body in about a second or something like that. Okay, what about a whale? Similar dimension. Okay, so it's going to be something like 10 meter per second. Okay, that's the typical. Okay, now I want you to calculate what is the Reynolds number that is associated. I want you to calculate what is the Reynolds number that is associated with the motion of these objects in water. Okay, that's the question. So how do we go about doing it? Can you just do that? Just plug in all these numbers. I would like you guys to tell me the Reynolds number that is associated with the motion of these three different objects, which have different length scales, which have a different velocities with which they are moving. I would like you guys to calculate these numbers and tell me what is the Reynolds number that is associated with the motion of these fluids, these particles. Yeah, can you do that quickly? All of you know, right? The definition of Reynolds number, all of you know. Okay, Reynolds number is okay, it is defined as inertial forces divided by viscous forces, right? That's what you learned. And okay, typically it is defined as rho v bar, some length scale by viscosity, right? That's your definition of Reynolds number. So can you calculate what is the Reynolds number? So mu is the viscosity of the fluid, right? So that's given to you, right? What about rho? Rho is the density of the fluid, that's also given to you. What do you say about d? D is your characteristic dimension, right? When you talk about flow through a pipe, typically d is going to be the diameter of the pipe, right? Now because we are interested in looking at the motion of objects in the fluid, okay, that d should actually be the diameter of the particle, okay, because the relevant length scale in this case is the size of the object or the dimension of the object which is swimming in a fluid. Therefore, your Reynolds number definition, your characteristic length scale is going to be dp, which is the diameter of the particle. Okay, that's one modification that you would have to do for the Reynolds number formula that you learned. What about V bar? Again, flow through pipe problem, V bar is your average velocity with which the fluid is flowing through the pipe. However, in the case of fluid particle systems, okay, if you have an object which is moving in a, like say a stagnant fluid for example, then your V bar is going to be the characteristic velocity with which the particle is moving in the fluid. Okay, so with this you should be able to get what is the Reynolds numbers, right? Can someone tell me what is the Reynolds number for case 1? Was that 10 power? Oh, there are 10 power 8. What about the next one? 10 power 6. 10 power minus 5, right? Now you also learned a little bit about laminar flow and turbulent flow, right, in the class so far. So now there are certain range of Reynolds number for which you are going to consider the flow to be laminar flow. There is going to be a range of Reynolds number for which there is going to be a transition regime, and of course there is going to be a range of Reynolds number beyond which your flow is going to be turbulent flow, right? And when you talk about flow through a pipe, right, if you have like say fully developed flow, your parabolic profile and all that, what is your Reynolds number for laminar flow conditions? What is that? approximately about 2000, right? Anything that is less than, okay, or equal to 2000 is going to be, it depends on textbooks. So McCambie Smith is 2100, so it's about 2000. Anything less than that is laminar flow. What about turbulent flow? That is your laminar flow. Something about 4000, right? Anything about 4000 is turbulent flow. In the case of fluid particle systems, so these numbers get a little shifted. Okay, so typically when you refer Reynolds number in terms of a RE with P at the as a subscript, that means it's a particle Reynolds number. If the particle Reynolds number is less than 1, that is your laminar flow condition. If your particle Reynolds number is greater than 1000, that's your turbulent flow condition, and anything in between is going to be your transition regime. Okay. Now, if you look at the flow through pipes and problems where you had fluids flowing through conduits, your transition from laminar to flow, it is actually governed by your velocity of the fluid, viscosity, the parameters, right? However, it turns out what you have is a case where you have everything which is basically moving in the same fluid, right? You have your fluid in which the objects are moving is fixed, that is your water, okay, with a given density and viscosity. However, all that you changed was the object, right? You had a whale swimming, a human and a bacteria, and you can look at the Reynolds numbers, right? They are markedly different. Okay, therefore, the flow around objects, okay, are going to be very different than the flow in pipes. Okay, and so typically when your Reynolds number is less than 1, you can think about it as a laminar flow conditions, and depending upon the fluid object combination that you're going to look at, okay, the object is going to experience very different kind of flow field around it. Okay. Now we will move a little bit into, so we're going to take a simple case of fine particles, okay, in a fluid. Okay, what I mean by fine particle is, so I have a container, I have particles, okay. The dimension of these objects, if I were to think about dimension of these objects, is going to be in the range from about 1 nanometer to 1 micrometer. Okay, that's the dimension of the object. So typically people call them as colloids or nanoparticles, right? If you remember the movie that I showed a couple of classes ago, so there was a movie in which you had objects which were kind of moving around, right? And so now if you take such tiny particles and if I put them in a fluid, I'm going to ask a question as to what are the different forces acting on the particle. I have tiny particles which are in a fluid, okay, and I would like to have an idea about what are the different forces that are acting on the particle. Can you name some forces? Of course, the first one is going to be obviously gravity, right? Your gravitational force. Okay, so if you call it as Fg, okay, that is going to go as delta rho, that is a density difference. Okay, delta rho is your rho p minus rho of fluid, okay, where rho p is the density of the particle and rho f is the density of the fluid times volume of the particle, right, times the gravitational constant, right, your g, acceleration due to gravity, right, that's your gravitational force. Any other force? What is that? Somebody says drag force. Do you think there's going to be a drag force? So you have learned that the drag force comes into picture whenever there's a relative motion between the particle and the fluid, and especially when you take these tiny particles, 1 nanometer or 1 micrometer particle. So it turns out they were moving around, and that moving around was because of what is called as a Brownian motion, right? And whenever there is a relative motion between the particle and the fluid, your drag force is going to come into picture. People call it as drag force. There's also another term for it. It's called as a hydrodynamic force. You can also call it as hydrodynamic drag, okay? And that, if you say it as FD, any thoughts? What is the functional form for this? I'm sure all of you have learned this at some point. It is 6 pi, okay, mu, which is the viscosity of the fluid, some average velocity which the particle is moving, and your r, okay, or rp or whatever, right, your size of the particle, okay, that's your drag force. Any other force? So there's gravity, there's drag force. Any other force that you think is important? What is that? Friction. Friction, drag, they're the same, no? When people also call this as frictional forces, if you want to write another name. Okay. Other one is what is called the Brownian force. Okay, and this Brownian force, it goes something like, it's Fb, it goes as kBt, that is your thermal energy, divided by Rp. Okay, so kb is something called as a Boltzmann constant, right? And T is your absolute temperature. Okay, the value of kBt is something like 1.38 into 10 power minus 23 joules per Kelvin. Okay, let's think about again calculating these forces. Okay, I would like you guys to calculate what is Fd. Okay, so if you take let's think about a simple case of 1 micrometer particle. Okay, like this is going to be your Rp. Okay, and again let's go back to your viscosity of the fluid is 0.001 Pascal second, or 1 into 10 power minus 3 Pascal second. Your density of the fluid is again 1000 kg per meter cube. Okay, let's take a particle with a density of, like, say 1100 kg per meter cube, and if you take a 1 micrometer particle, typically it is known that it kind of moves around with a velocity which is the order of 1 micrometer per second. Okay, that's a typical. Okay, if people have done these measurements, so what they have done is they have taken a microscope, they have observed the velocity which the particles move, and that typically for a 1 micrometer radius particle is of the order of 1 micrometer per second. If you put in all these numbers, can we get values for, say, Fg and Fb? Can you just quickly work it out? What's that? Volume is 4 by 3 pi r cube, right? So you know the dimension of the particle. You can actually calculate what is your volume of the particle. What are the numbers? Yeah, somebody has the numbers. What is Fg? So this should be of the roughly 4 into 10 power minus 15 newtons. This also should be of the order of I don't know if you have these numbers. Let me just quickly check. Yeah, so the number that you will get would be your drag force is of the order of 4 into 10 power minus 15 newtons, and your Fb would also be of the similar order. Okay. Now, so what I can say from this calculation is that if you have a particle of 1 micrometer radius and if it is immersed in water, okay, and if the density difference is about 100 kg per meter cube, it turns out that your Fg and Fb, they are comparable, right. Now, what happens if I reduce the size of the particles? If I have, like, say, instead of 1 micrometer, if I take, say, 10 nanometer particle, okay, obviously what you will see is you will see that your Fb, okay, which is the Brownian force, is going to be much greater than F gravity, right. Okay, therefore, so whenever one is working with fine particle system, it's a good idea to kind of think a little bit about different forces that are acting and also do a simple calculation of the different force that will be acting on the particle. That will give you some information about whether your gravitational forces are really important in terms of making your dispersion or the fine particle dispersion unstable. Okay, whenever when I drew this picture, right. So now whether the particles continue to remain in the solution or they would go back and sit at the bottom, that would depend on the balance between the different forces that are acting on the particle, right. Now, there is a gravitational force which wants to pull the particles down, okay, and you have Brownian which wants to keep it in a suspended state, right. Therefore, if you go for finer and finer particle sizes, it so happens that your Brownian force overweighs the gravitational force. That is one of the nice way of imparting nice stability for the particle dispersion that you are working with. Okay. Now that we know a little bit about fine particle dispersions and different forces, now I am going to ask a question as to, so I said that these fine particles, they exhibit Brownian motion, right. Do you think there is any practical use of this chaotic motion that the particle exhibit or the fine particles exhibit when you put them in a fluid? Do you think there are any applications of it or any uses? Anyone has read a little bit about Brownian motion? You read it at some point for sure, right, in your +2 or maybe before that, right? So it turns out that the concept of Brownian motion was really useful, okay, and also it is useful. You can use this for actually measuring particle size, okay, number one. Number two, people have also used this Brownian motion to actually prove the existence of atoms and molecules. Okay, before there was a debate about whether the molecules are there, atoms are there or not. Okay, so people kind of use some nice simple experiment that they could do by monitoring the Brownian motion of particles in a fluid, and they were able to kind of come up with a explanation for the fact that the molecules do exist. Plus, have you heard of Avogadro number? Right, so we know that 1 mole of any substance has 6.023 into 10 power 23 number of atoms, or right, or molecules, right. Now, one of the proofs for the calculation of Avogadro number, it actually came from measuring the Brownian motion. Okay, what someone called John Perrin, okay, he's a French scientist. What he did is he used this Brownian motion concept, and from that he was actually back calculated what is called as a KB, okay, which is the Boltzmann constant, and there is a relationship between Boltzmann constant and R, which is the universal gas constant, and your Avogadro number. Okay, so he used that to back calculate what is the Avogadro number. It turns out that the number that he got was very close to what is known now. Okay, so we'll talk a little bit about these concepts in the next class. Okay, so I'm going to start with showing you again some more videos of Brownian motion. Okay, explain a little bit about why is it important, and what kind of measurement that people did, and then we're going to derive one very important equation, which is what is called as a Stokes-Einstein's equation. Okay, Stokes-Einstein's equation, which is one of the fundamental equations that people use for measuring the particle size data. Okay, so we'll talk a little bit about that in the next class. I'll stop here today. Yeah.